Hello, I'm Stefano Lambertenghi. Thank you for your interest in our work.
When testing a self-driving system, the most accurate way is to do real-world testing. This is because the environment in which we evaluate the system under test is the same in which we will deploy it. But at the same time, this comes with a few negatives, especially high cost due to the organizational aspect and the time involved in testing in real world. At the same time, if we want to test something that includes obstacles or, for example, pedestrian, we have a risk factor to keep in mind. And at the same time, we are constrained by the environmental conditions and the scenario in which we place the vehicle, such as weather effects. It is for these reasons that simulation-based testing has become more and more prevalent. It solves all of the problems of real-world testing, but at the same time, simulation is an approximation of reality. The resulting effect is the reality gap, which is the difference between real-world sensors, physics and scenario, and the simulated ones. This results in a difference of behavior. We call this the behavior gap. In more details, the sensors gap results in a perception gap, where the simulated and real image, LiDAR, or other sensor feed do not represent exactly the same content. This is highly problematic, especially for deep neural networks, in which different textures or features might create different outputs into the perception system. The physics gap, also known as the actuation gap, is due to differences in physics between real world and simulation. This could cause a certain steering and throttle input to have different effects in behavior between real world and simulated scenarios. Finally, the scenario gap is due to the complexity of recreating exactly the same conditions that we have in the real world in simulation, such as exactly the same actors, the same backgrounds, or the same geometries. These differences could cause different outcomes in testing scenarios between simulation and real-world testing. And it is for this reason that literature has proposed multiple ways of mitigating these types of gap. From right to left, in terms of complexity, we have simulation in the loop, the most basic condition, our baseline, in which both the sensors and the actuation are simulated. Effectively, also the scenario is simulated as a consequence. Then we have vehicle in the loop, in which we track the position of the real vehicle, position the vehicle in simulation, collect sensor data from simulation, and react to this. This should mitigate the actuation gap, but keep the perception gap unchanged. Then, the most complex version is mixed reality testing, in which the data that comes from the sensors is a mixture between real-world feeds and simulated feeds. An example would be to add some obstacles or actors from simulation into the real world, effectively having real perception, real actuation, but having the flexibility of changing the scenario such as we can do in simulation. Finally, we have real world as our goal condition. In our work, the main goal is to understand the ability of simulation in the loop, vehicle in the loop, and mixed reality to mitigate the behavior gap, the actuation gap, and the perception gap.
For this work, we decided to use the Donkey Car small-scale vehicle platform. As it is open source, it already provides most of the components that are necessary for our evaluation. It already has an 8-megapixel Sony camera. It has a Jetson Nano board that connects to our framework. It lets us to send commands to the vehicle, but at the same time to send the data, such as the camera or the LiDAR, to the framework. Now, the camera is there, the LiDAR is not. We used an iPhone 15 Pro as it has a time-of-flight sensor. Using a Record 3D open source app, we get the time-of-flight data, convert it into depth data, and send it via Wi-Fi through the framework of the car to our mixed reality framework. This enables us to receive both camera and LiDAR data directly in real time, while at the same time, we have the same type of data coming from the simulator. Now, for the simulator, we have decided to use Unity and the SimDonkey Car digital twin. This has already been created together with the platform, but we have augmented it to enable us to do vehicle in the loop and mixed reality testing. It has two digital twins of our trucks, one you already saw, and one that you can see in this picture above. The scenario you see above is the nominal condition, as it is a rather simple room with not a lot of background noise. This should be easier for our perception systems, but at the same time, the truck geometry is a little bit more challenging. We decided to create quite a few different turns, and one in particular is at the limit of the steering range of the car, while the room that you see me in is our generalization room. The truck is simpler with two straights and two turns, but at the same time, this truck has a lot of background noise. You can see we have computers, we have big windows, and also we have a lot of other demonstrators in this room. So for that reason, we expect the perception systems to have a rather challenging time. And especially you can see the pillar behind me. This is in close proximity to the truck. And it creates a very challenging condition, especially for the LiDAR perception system. Once we have created a testing scenario, we obviously need systems under test. For that, we have decided to take two different paradigms, which are widely used in both research and industry. An end-to-end model, in this case based on NVIDIA's Dave2 architecture, and a modular pipeline. The end-to-end model transforms directly images into driving commands, such as steering and throttle, while the modular pipeline takes as input LiDAR, localization, and map, and in the first step, does the perception, which transforms the LiDAR point clouds into bounding boxes of where the obstacles are relative to the vehicle. The second step, the planner, takes that information together with the map and the localization to understand what is the most feasible path to traverse the street and to avoid obstacles at the same time. Finally, the control module helps us to transform the waypoints that are created by the planner into actionable commands, such as the steering and the throttle output as the Dave2. To properly evaluate the four testing domains, we need to have a perfect mapping between real world and simulation. To do that, we create a framework that uses 4 infrared tracking cameras to detect the position of objects and the vehicle in our real-world scenarios. Also, we have a digital twin of the environment in a Unity-based simulator. And with that, we are able to map the position of real-world objects to the simulated world. With that, then, we can compare properly a scenario in which the obstacles are positioned exactly the same way, and enables us to do vehicle in the loop testing in which the real vehicle is moving, but the camera is simulated, and mixed reality, in which the camera is a mixture between the real world feed and simulated feed. For example, the obstacles might be simulated.
In our empirical evaluation, we answer 3 research questions. First, we consider the behavior gap. How different is the behavior of the system under test across both nominal and generalization scenarios in terms of different testing domains? In research question 2, we delve deeper into how vehicle in the loop mitigates the difference of actuation between simulation and real world. And finally, in research question 3, we consider the validity of the mixed inputs and also how much they improve the perception gap compared to simulation only. Now, I wouldn't want to spoil it for you, so if you're interested in our empirical evaluation and in our findings, please click the link below to see our paper and our results. Thank you for your attention.